Hello, class. Hope all is well. Today, I am going to work in Module 3. We're going to be looking at the second section where we are diving deeper into exponential functions, solving exponential equations, logarithmic functions, expansion and condensing exponential and logarithmic functions. 3.2 in pre-cal today. I will likely turn my camera off as I'll be sharing my screen, and we'll get started. So let me begin by turning on my document camera screen so that I can share with you. Okay, I'm going to zoom in here. And as I stated, we are looking at 3.2, the second section of 3.2 on today. So we'll be exploring more properties of logarithms and exponential functions, and we'll look at logarithmic equations, things of that nature. So let me begin here with a few common log properties. And we saw a couple of these in the first section, but they dive a little deeper here in this section. You may recall this one where we had a log base b, and then we were taking the log of an exponential with that same base b. So what happens is the log base b and the b in the exponential cancel each other out to leave us with just x. Likewise here, notice that there is no index, but when there is no index, no log base shown is understood to be a base 10. So therefore the log base 10 and the base 10 in the exponential cancel out to leave us with just x. Here you've got the exponential raised to a log. So you got the you got the exponential base b, and then raised to a log base b, same base. So they cancel out to leave us with just x. And then you've got a base 10 exponential raised to a log base 10. Remember, when there's no log index shown, is understood to be a 10. So the base 10 in the exponential and the base 10 in the log cancel out to just leave us with x. So these are inverse properties, basically because exponential and logarithmic functions are inverses of each other, so they undo each other. Then you've got a couple of other general properties. The log base b of 1 is equal to 0. This is because we're trying to determine b raised to the 0 power equals 1. Remember, when you're evaluating logs, you can essentially think of them as exponential in form. So this would be, if you were to rewrite this in exponential, it would be b raised to the 0 power, and that would equal 1. So in other words, b raised to what power produces 1? B to the 0 power produces 1. So log base b of 1, no matter what that b is, because it can be anything, any number raised to the 0 power would be 1. Here, you would have a base 10, again, similar to this. It's just that the base is not shown, and when it's not shown, it's understood to be a 10. So 10 raised to the 0 power would be 1. Or in other words, log base 10 of 1 is equal to 0. Here, log of 10 equals 1. So this is where you've got a base 10 log. Or better yet, it's maybe easier to look at it in this format first, where b and b are the same, and they just basically equal 1. So in other words, b raised to the first power is just b. Or in other words, anything raised to the first power is just itself. Okay? So this would be 10, base 10, raised to the first power would just be 10. Okay? So just some common properties that I wanted to mention. So, same thing can occur when you're dealing with natural logs. Remember, we have common logs, that's a base 10. A natural log is a base E, okay? So LN is our shortened format for a log base E. That is the same thing as just LN, okay? So a natural log, in other words, a log with a base E is just LN, the natural log. And so these properties also apply to natural logs, as you can see right here. So LN of e to the x power, the ln and the e cancel out to leave us with just x. Okay. All right. So let's look at some rules because we're going to be looking at expanding logarithmic functions. Let's look at a few rules that will apply. So you know that we've got the product rule for exponential functions. Well, because logs are inverses of exponential, we have a product rule for logs. And let's examine that here. So this is where it says let b, m, and n be positive real numbers, because remember you can't take the log of a negative. So we understand that they're positive real numbers, and this is where b is anything other than 1. Okay, so log base b of m times n. So log base b of a product is the same thing or is equal to or equivalent to the log of their sum. I'm sorry, the sum of their logs. So we can break that product apart and write these as a sum. This would be an expansion. It would be an expansion of a product to a sum. So it's as if you're basically kind of, if you want to think about it, in a sense, distributing the product mn, distributing the log through that product. So log base b of m plus log base b of n. So product coincides with addition. You're adding the logs. So the logarithm of a product is the sum of the logarithms. Okay? So when you see a product, we can expand those by writing those as a summation. And we will, of course, look at some examples. A second property is the quotient rule. We'll look at a quick example here. So here we're using the product rule to expand. So we've got log base 6 of 7 times 11. Now, keep in mind, once we expand, if we're able to simplify it at that point, we would. And when I say simplify, I mean you're able to take the log of that, the log base, whatever base it is of that constant. If you're able to do that and get a whole number, then you would simplify it. You would go ahead and write it more simply. If not, we would leave it in this form. So we've got log base 6 of 7 times 11, okay? So that means we can write this as a sum. This is where we're using the product rule to expand the logarithmic expression. So this product would become a sum. So this would be log base 6 of 7 plus log base 6 of 11, breaking them apart. Now at this point, you always want to check, and of course you have your technology that you can use, but you always want to check by asking yourself, is there a number that I can raise 6 to and get 7? 6 raised to what power would give me 7? There is not a number, not a whole number anyway, okay? Maybe some 1.234, whatever, some decimal perhaps, but we wouldn't want to simplify that and write it as some lengthy decimal. We'd rather just leave it in this form. Same thing here. Is there a value that I can raise 6 to? Is there an exponent that I can raise 6 to and get 11? No, not a whole number, it is not. So that is all the simplifying I can do here. Let's look at this one. Here we've got log of 100x. And understand, of course, this is a log base 10. When there's no index, when there's no base shown, it's understood to be a 10. So this would be log of 100 plus log of x. Now, log of 100 can be simplified, okay? Now, of course, like I said, you've got the technology. And I will put this in my calculator to just demonstrate that. So log, and remember, because it's a base 10, I can simply smear here. I can simply get that glare off too. I can simply press the log key. The log key is right here. And then just enter 10. Now, I want you to have an understanding of why this is, I'm sorry, 100. I entered 10. That's 100. Log of 100. I want you to understand or have an understanding of why this answer is 2. The reason it's 2 is because you ask yourself, 10 raised to what power would give you 100? And that would be 10 to the second power. Okay, the base is 10. So that would be 10 raised to what power would give us 100. So that's where the 2 is coming from. Now, of course, this is a variable, so we would just leave that. So the answer, the final answer here would be 2 plus log of x. Okay, and we will look at some examples. I'm going to wait until I look at each property individually because I think a few of these may take a couple of the properties and put them together. Well, not really. We can actually look at number 3 and number 4 if we want to. So I am looking at homework 3.2, okay, that matches with the section. Let's go ahead and look at 1 and 2 here as well. Number 1 and 2, it says evaluate the expression without using a calculator. Nobody's going to know if you used a calculator or not. So if you're wanting to be sure that you get the correct answer, use your calculator. I do want you to have an understanding of it though, okay, of what the answer, of why the calculator produced that particular answer, okay? So here, these are what we call inverses of each other. The natural log and then the base e cancel each other out. And so that's where we just get an answer of 2 here. But put it in your calculator if you're ever unsure. Here you got ln, and then you've got e. Notice that the ln has a second function right here, the e to the x power. So to get e, you need to press second ln, and then that is raised to the second power. Okay, so ln of e squared. Yes, the calculator does impose parentheses, whereas here there aren't any, but it does not matter. The answer is 2. Okay. Similarly here, ln and base e cancel out, and that just gives us 5x. Now, of course, you can't put the x in the calculator, and the calculator actually give you a number, but we could put in ln of e to the 5th, and that we know would be 5, and then just carry the x down, okay? So those are the inverse properties. Now, number 3 is our first look at the product rule. Notice that it does not tell us which rule to use. It just says use properties of logarithms to expand. So you have to recognize that this is a product, and therefore we're going to apply the product rule. So this is log base 5 of 13 times 3, log base 5 of this product. So to expand it out, and then it says, where possible, evaluate the logarithmic expressions without using a calculator. So in other words, where possible, if you can simplify it and get a whole number, you want to go ahead and do that. First thing we'll do is expand it out. So this becomes log base 5 of 13 plus log base 5 of 3. Now, if we're asked to simplify this without a calculator, then that means we would have to be able to express 5 to a number, 5 raised to a power, to produce 13. Or right here, 5 raised to what power would produce 3? There is not. There is not one. The only way that we could get an answer here would be using a calculator to get some sort of decimal. So because there is not a whole number that would simplify for either of these, we leave them as is. Log base 5 of 13 plus log base 5 of 3. Okay? Number 4, use properties of logarithms to expand the logarithmic expression as much as possible. So again, this is another expansion problem. Look at what's taking place here. This is a product, 10,000 times x, log of 10,000 x. So this is a product, which is log of 10,000 plus log of x. Now, understand that when you do not see a base, it's understood to be a common log base 10. So in other words, I'm trying to find 10 raised to what power, which would give me 10,000. Notice that there are 4 zeros here. So that would be 10 to the 4th power would give me 10,000. Okay? So, but always you could put it in your calculator as well. If you're having to use the change of base property, then it would be log of 10,000 divided by log of 10 and get 4. Or if you have that special key on your calculator. Remember, to pull it up, I press alpha window, and then I go down to number 5, yep. And I have a 10, base 10, and I'm taking the log of 10,000, and I get 4, okay? So log base 10 of 10,000, in other words, 10 raised to what power would give me 10,000? That would be 4, and then plus log of x. And of course, you have to just keep the log of x because you have a variable there, okay? So number 3 and number 4 were the product rules, okay? Look at number 5, it's a bit different. So let's go back to our notes for just a minute here for number 5, before we look at number 5. The quotient rule. Notice this time it was not a product. It is a fraction, which is a quotient. So again, b, m, and n are all positive real numbers. Log base b of m divided by n, a quotient, can be expanded to be a difference of two logarithms. So log base b of m, the top, minus log base b of n. You always write the top first, minus the bottom. So we're taking a quotient and we are expanding it out to be a difference of two logs, okay? So let's look at number 5 and number 6, and maybe even number 7. I think all of these apply the quotient rule. Look at number 5. All right, number 5, using the same directions, using properties of logs to expand. Again, it does not tell you which property to use, so you have to recognize which property needs to be used. It's a quotient, okay? It's a fraction, so we're applying the quotient rule. And when we apply the quotient rule to expand, that means we are changing a quotient to a difference of two logs. So this would be log base 4 of 4 over y. That would become log base 4 of 4 minus log base 4 of y. Okay, and I put a curve on my y so that it doesn't look like a 4. So here you've got a base 4, and then you're taking the log of this value 4. So in other words, 4 raised to what power would give you 4? That would just be 1. 4 to the first power is 4. So log base 4 of 4, that would just be 1. And then you have minus log base 4 of y. Because that's a variable, nothing else we can do there. So if you're able to simplify it and get an actual whole number, then you would do so, which we did, okay? Look at number 6, same directions. Log of y divided by 100, or log of y over 100. So this would become log of y minus log of 100, okay? Log of y is log of a variable. It's just going to stay log of y. And remember to understand that this is a base 10, but it's a variable, so there's nothing we can do there. So we just keep log of y. Now, right here, log of 100, this is log base 10 of 100. Okay, so I'm going to put a little arrow here. Log base 10 of 100. So you ask yourself, or you put it in the calculator, 10 raised to what power would give you 100? That would be 10 to the second. So this becomes 2. Log base 10 of 100 is just 2. So our answer would be log of y minus 2. And there's nothing else you can do here because you cannot simplify this any further. You cannot combine that. Nothing else we can do. Okay? And again, if you wanted to verify that, log of 100 in your calculator, just press log. Because it's a base 10, you don't have to worry about the base. It's understood to be a base 10. Just enter in 100. So 10 raised to what power? 10 raised to the second power will give you 100. Okay? Another example with the quotient rule, number 7. Use properties of logs, same directions, okay? Again, they do not tell us which property to apply. I recognize this is a quotient. So log base 4 of 256 divided by y. So first thing I'm going to do is expand it out. Log base 4 of 256 minus log base 4 of y. So we know this is the log of a variable, so it's just going to stay. But this first part, we want to see if there is a power that we can raise 4 to, what number we can raise or show 4 raised to get 256. Now, if you can't think of that off the top of your head, don't hesitate to use your calculator. So remember, if you got the shortcut key, you press alpha window and you go down to number 5, and I'm going to get it out this glare. Let me scoot that down. And then the base is 4. The value that we're taking the log of is 256. And that gives us 4. So 4 raised to the 4th power is 256. So when you're evaluating the log, you say 4 raised to what power gives us 256. So log base 4 of 256 is 4. And then we have minus log of base 4 of y. Okay? So far, so good. I'm hoping, but I'll make sure that I allow time in class to go over any questions that you have, okay? All right. Let's take a look at another property. The power rule. And we talk about each of these rules individually. There'll be a few problems where you look at them each individually, because in a second or two, you'll see examples or problems that you have to simplify where you're applying several or maybe even all of the properties together. Okay, so here is the third rule called the power rule, and it means exactly what it says. You will see within a log, you will see whatever the base is, the value raised that you're taking the log of, that value, it will be raised to a power. So if we're trying to simplify it, in order for us to simplify or evaluate a log, we typically have to eliminate that power. And so what that means is we bring down that power, the log of a power, we express it as a product of that exponent times the logarithm of the number. So the logarithm of a number with an exponent is equal to the product of the exponent and the logarithm of that number. So you basically take down that power, bring down that power in front of the log expression and show it as a product. So then we're able to evaluate the log and then multiply that answer that we get, if we are able to, by that power. Okay? That is the power rule. Let's look at one or two here in the notes, and then we'll look at the homework. So take a look at this first one. It says, use the power rule to expand. I'm going to cover this up so that you can see it a bit better. So we have log base 6 of 3 to the 9th power. In order to evaluate a log, I would first, because I would love to be able to evaluate the log base 6 of 3 if possible, but I got to first get rid of that exponent. So I write this down as a product of the exponent and the log. So I bring down that 9 and show it written in front, and understand that that means 9 times because there's no symbol in between. So this would be 9 times the log base 6 of 3. Now, if I could simplify this log base 6 of 3, I would, but there is no number that I can raise 6 to and it produced 3. So you ask yourself, 6 raised to what power would give us 3? There isn't one, not a whole number anyway, okay? Some approximate decimal perhaps, but we want an exact value and there is not one. So we would leave it like that. Here's another one. Right now, first off, this is written as the natural log, the ln of the cube root of x. So if you're trying to evaluate a log, you got to first get rid of this radical that's around the value. So I would first begin by expressing that cube root as a rational exponent. Okay? So that ln of the cube root of x becomes ln of x to the 1/3. A root is the same thing as a rational exponent. Okay? So this is ln of x raised to the 1/3 power. Then I apply the power rule, which allows me to bring down that 1/3 in front, express it as a product of 1/3 times ln of x. And of course, there's nothing else I can do here because that's a variable. Third one here, this time you've got the log of x plus 4 squared. So this whole expression is squared, okay? Now, I'm going to start by taking down the exponent. Instead of it having a 2 in the power, I bring it down as a 2 in front to show it 2 times log of x plus 4. If this had been, instead of x plus 4, if this had been maybe x times 4, then I would be able to expand this even further with the product rule. But because this is a sum, there's nothing else I can do here. And that will be the answer. Okay, so let's look at a few here. Look at number 8. Same directions. It does not tell you which property to use. So you have to know what property to apply. I recognize that this is a power. So this is log base A of x to the third power. So I apply the product rule. I bring down the 3 and I show that as a product of 3 times log base A of x. Nothing else I can do there. That's my answer. Okay. Look at number 9. Log of b to the negative 4th power. And understand, of course, this is a base 10. This technically is a base 10. So log of b to the negative 4th power. I would first bring down the negative 4 exponent. So that would be negative 4 times log of b. If b had been maybe 10 or 100, I would evaluate it even further. But because this is a variable, there's nothing else I can do. Negative 4 times log of b. But understand that I do not see a index, a base. It's understood to be a common log base 10. Okay? Now, here we go. Number 10 is where we're going to start applying several of the properties together. So let's just summarize here before we jump on to number 10 and 11. Here are the properties just on a slide together, simplified here. Product rule, quotient rule, power rule. So there will be problems where you have to apply maybe 2 or perhaps all 3 of these properties, okay? So the product rule, you'll notice that you'll see a product. You can expand it out as a sum. Quotient, you'll notice if you see a fraction or quotient, you can expand that out as a difference. And then if you see a power, you can write that as a product of that power times the log expression. Okay? So let's look at number 11 here, or number 10 here. So we've got log base b of z to the 5th times y. So the first thing I'm going to do is recognize that I have a product, okay? So because I have a product, the first thing I'm going to do is break these two expressions apart, write them as a sum. So this becomes log base b of z to the 5th plus log base b of y, okay? I'm not quite done, even though these are variables and I won't be able to simplify them much more. I have an exponent here. I always want to expand it out as much as possible. So I'm going to pull out that exponent, express it as a product down front in front of the log expression. So this then becomes 5 times log base b of z plus log base b of y. Don't forget to include that last part. Sometimes I'll have students that'll focus on the part that they're simplifying and they'll enter that in and forget about the other part. So just make sure you put in the whole answer. And that would be all that you're able to do because again, these are variables, nothing else you can do. Look at number 11. So with number 11, we've got a quotient. Okay, whereas here we started with a product. So the order is typically product rule, then power rule, or quotient rule, then power rule. The power rule is typically the last rule that you apply, okay, when you are expanding. Notice that these say expand. When you are expanding, notice that we applied the power rule last. We first wrote them as a sum, then we applied the power rule. So I'm going to do the same thing here. I'm going to first write this quotient as a difference, and then I'll apply the power rule. So log base 4 of 64 over the square root of x plus 2. So this becomes log base 4 of 64 minus log base 4 of square root of x plus 2. Okay? Now, I am going to see if I can simplify this even more in just a minute, but the first thing I'm going to do is make sure I apply all my log properties first. And right here, I do not want to leave that as a square root. So I'm going to apply that, or I'm going to rewrite that as a rational exponent. So I'm keeping the log base 4 of 64 for a minute. And this becomes log base 4 of x plus 2 to the 1/2 power. Okay, let me zoom out just a bit here. So I rewrote that radical, and understand that when there's no index, we know that it's a square root. So a square root can be written as a rational exponent of 1/2. A cube root can be written as a rational exponent of 1/3. A fourth root is 1/4. A fifth root is 1/5, and so on. So a square root is 1/2 power. Okay. Now I am going to clean that up a bit more. So I'm still hanging on to the log base 4 of 64. This power comes down as a product. And then I have times log base 4 of x plus 2. Okay. Now that is a plus. So I cannot expand that any further. If it had been a product like x times 2, then I would. But that is a plus. Now, almost done. Last thing, is there a power, is there an exponent that I can raise 4 to and I get 64? In other words, ask yourself, 4 raised to what power gives you 64? If you're ever unsure, put in your calculator. So that would be, if I use the shortcut key, that would be, let me get it out the glare here, log base 4 of 64. Let's see what we get. 3. 4 to the 3rd power is 64. Okay. Remember, if you don't have that shortcut key, you can put it in as log of 64 divided by log of 4. And it'll give you 3. Okay. So 4 raised to what power gives you 64? 4 to the 3rd power. So log base 4 of 64 would be 3. And then we have minus 1/2 log base 4 of x plus 2. This whole thing here is your answer. Nothing else you can do. That is your answer. You cannot simplify that any further because it's x plus 2. So that is your answer. 3 minus 1/2 log base 4 of x plus 2. Oh, also, let me say this. When you are using, when you're entering these answers in on the computer, be sure that you're using their log keys. If you're using, like, if you're typing on your keypad, your keyboard, log, I'm not certain that they will understand that notation. So when you're on the problems, you notice the little different key functions. There's like a little bar at the bottom of the screen that will pop up to allow you to choose whether you need an exponent, whether you need a square root, whether you need a ordered pair. You know, it gives you all the options that you may need to express your answer in. Make sure that you use their log key there, because I'm not certain if you use the log keys on your keyboard, if the computer will recognize it. Okay. On mine, on one problem, it didn't. And then on another problem, it did. So I don't want you to be confused with that and wondering, well, I have the right answer. Why did it count it wrong? Because it may want you to use that specific log key. Okay. I just wanted to say that. Okay, so up until this point, we have been expanding. Notice that all of these directions, or all these, all these directions, what you're supposed to do on each of these problems said expand. What if we want to work in reverse? Notice on the next few problems, it says condense. Okay, so number 12 and 13, the directions here say use properties of logarithms, those same 3 properties: product rule, quotient rule, and power rule. But this time we're going to condense the logarithm expression. So we might be given a sum, and we might be asked to write that sum as a product. So let me pull up the notes and see if I have do. So take a look here. Notice it says properties for condensing. They're the exact same properties, okay? It's just instead of working from a product and going to a sum, you're going from a sum to a product. So you'll notice that the two expressions will have to have the same base, and they'll be separated by a plus. So log base b of m plus log base b of n. Because they have the same bases and it's a sum, you can express that as a single log of a product. Here, if you've got log base b on both of these, same bases, and they're separated by a different sign, a subtraction, then that difference can be expressed as a quotient of the values. And then here, if you notice that you've got a constant multiple here out front, a constant multiple or constant value here multiplied in front or times the logarithmic expression, that can be condensed back up into the exponent, written as an exponent, okay? So here's one. We've got log of 25 plus log of 4. So notice that they do not show a index, a log base. It's understood to be a 10. Log base 10 of 25 plus log base 10 of 4. Okay, so we're able to combine this as a product because they have the same base. So log base 10 of 25 times 4. So 25 times 4, if we're able to go ahead and multiply that together, they're both constants, so we can. So we're going to go ahead and express that as simply 100. So now we're looking for the log base 10 of 100, or log of 100. So 10 raised to what power would give you 100? 10 to the second power. So log of 100 is equal to 2. Okay? Here, you have log, on this example, you have log of 7x plus 6 minus log of x. So you got the same log expression, same base 10 on both of these. Log base 10 of 7x plus 6 minus log base 10 of x. So this difference of these two logs can be expressed as a quotient of these two expressions. So you keep the log and you express these two values as a quotient, 7x plus 6 over x. Now you might ask, well, how come I wasn't able to do anything here? Well, it's a sum and it's an expression here contained in the parentheses. We're not trying to expand it. It's already together as a sum, so there was nothing to do here, okay? And then also, even if you were trying to expand it, that would have had to been a product, and that's a plus. So there's nothing else you can do there because these are variables, so you just wrote it as a quotient. All right. Then you've got this one and it's asking you to write it as a single logarithm. You're condensing it to a single logarithm. Notice that I've got a product in front of ln of x here. Okay. And then I've got, something was left off. That ln was left off right here. That should be ln. I apologize for that. So this is supposed to be 2 ln of x plus 1/3 ln of x plus 5. The ln is missing right here in front of that x plus 5. So the first thing we do is we take the products and we write them back in the exponent. So that 2 that was brought down is now written up in the exponent, ln of x squared. That 1/3 that was brought down is now written up in the exponent as 1/3. Okay? Then notice that we've got the ln, which is natural log, same base e, same natural log expression of a product, of a sum, and we're going to write it as a product. So this becomes, we're condensing it down, so this becomes the ln of x plus 2 times, and I just messed this all the way up. I put a 3 here. That's supposed to be a 5. Jesus. I apologize, you guys. So this becomes a product of x squared times x plus 5 to the 1/3 power. The last thing we can do, although this would be fine too, But the last thing we can do is, instead of keeping that rational exponent of 1/3, write that as a cube root. So this becomes the ln of x squared times the cube root of x plus 5, condensing it down. Right, so let's look at a couple of examples here, 12 and 13. And I think the problems in the notes are a bit more involved, a bit tougher than what you'll see in your homework and, on the test or anything like that. They're a bit more involved in the notes because you want that. You actually want a harder problem to learn, and then you just have to show that you understand it with a bit of a more simpler one. Look at number 12. This is a log 5 or log base 10 of 5 plus log base 10 of 2. Remember, there's no base, so it's understood to be a 10. So because this is a product, they have the same log base, we can express this as because this is a sum and they have the same log base, we can express it as a product. Log of 5 times 2. So this becomes log of just 10. And log of 10, well, that answer is just 1 because this is understood to be a base 10. So basically, you ask yourself, 10 raised to what power gives you 10? And that would be 1. But you can always put that in your calculator. Log of 10 is 1. Okay? So we express this sum as a single product. 5 times 2 is 10, so log of 10 is 1. Here we've got a sum, ln of x plus ln of 11. That becomes ln of x times 11, which is just ln of 11x. I usually want to express the number in front, and you may want to include your parentheses. I think it's going to automatically keep them anyway, but if it does not require it, ln of 11x is fine. I like to put the number in front, the coefficient in front. Okay? All right. I did introduce the change of base property. This is where number 14 is going to come into play. I did introduce the change of base property to you in 3.1, although it's discussed more in detail in 3.2 is where it actually came up. So these problems is asking you to use common logarithms or natural logarithms. What it's saying basically is the change of base property. Change of base property. So the reason it's asking you or introducing to you the change of base property is because here you would need a calculator. There is no number that you can raise 17 to. There's no exponent that we can put 17, that we can raise 17 to, and it gives us 11. 17 to what power gives us 11? There isn't one. So we would have to use the calculator here. Now, if you got that shortcut key, you can use it. If you got the log box key, the shortcut key, or the change of base, which would be log of m over log of n, okay? Either one of those. This is the change of base property. This is the shortcut key. So just recalling the change of base property, remember, I showed you this in 3.1, but it's actually really talked about in 3.2 here. So log base b of m, okay, this is where we basically can change it to a base 10, and we can simply say log base 10 of m over log base 10 of b. Change of base, okay? So when you use a base 10, the common log, you don't have to worry about putting in the log value. The calculator understands or assumes that it's a base 10. So that's what I'm going to do here. I'm going to apply the change of base property. So log base 17 of 11 would be log of 11 divided by log of 17. And that would give me, so I press clear that, I press the log key 11 divided by the log key of 17. And I get 0.84635. And of course, we'll have to round that because it's a recurring decimal, a decimal that kind of goes on Rounding that to 4 decimal places, this would be 0.8464. 0.8464. That 3 is followed by 5, which makes it go up to a 4. Okay? Now, if I have that shortcut key on my calculator, you can use that. So you would press alpha window, and you can actually put it in its original format with the base 17. So base 17 of 11, log base 17 of 11, 0.8464. Okay? So here's where you would need the calculator, because there isn't a number that we can actually express as an exponent for 17 and it give us 11. Okay? There isn't one, not a whole number. All right, let's see what else we got here. Another common log, number 15. Let me scoot that down here. Notice here we're even using decimals, so you most definitely would need the calculator here. Log base 0.1 of 20.4. So change of base would be log of 20.4 divided by log of 0.1. Or again, use the shortcut key. So if I've got the shortcut key, I press alpha window to pull it up. So my base is 0.1. And my value that I'm taking the log of is 20.4. And I press enter, and I actually get a negative number. Now, when you take logs, you can get a negative number, but you can't take the log of a negative number. So the answer can be negative, but the value right here cannot be. That's the difference. I don't want you to think that this is wrong. Remember, we had talked about the fact that you cannot take the logarithm of a negative value. You can't. However, when you actually evaluate a log, it's possible that this final answer is negative. Okay. All right. So we've got negative, around that to 4 decimals, negative 1.3096. Okay. All right. One last topic in this section deals with solving exponential equations. And that's what we're going to look at. There are 2 different ways depending upon what kind of exponential equation it is. Okay, so let's take a look at that. Right, so I'm on page 10 of my notes here. Solving exponential equations, first type, is by expressing each side as a power of the same base. So this probably would be for the easier exponential equations. This is where you can isolate each side, or you have basically 2 simple left and right sides of the exponential expression or the exponential equation, and you're able to write them, or they already come showing the base the same on each side. So if b to the m is equal to b to the n, if the same base is occurring on both sides, then we can eliminate the base and simply say the exponents are equal, m equals n. So if they are not already written with the same base, the first thing you will do is rewrite the equation in the form b to the m equals b to the n, where you got an expression with that base b equal to another expression with that same base b, whatever the base is. Once this is written in this manner, then you're able to drop the bases and simply set the exponents equal and then solve for the variable in the exponent. Because that's the kicker. When you're dealing with exponential equations, the variable is in the exponent and you're wanting to solve for the variable. So we have to somehow get it out of the exponent. And this method allows us to do so. So we're going to look at this method first, and then we'll look at some that can't use this method and what we have to do. So look at number 16 first. It says solve the exponential equation by expressing each side as a power of the same base. So they actually tell you what to use here. So we've got 3 to the x equals 9. All right. Now this side is already with the base of 3. There's nothing we can simplify or do here on this side. What we have to do is then look at the other side and say, is there a way that we can write 9 with a base of 3? Is there an equivalent way that we can express 9 where it is an exponential expression with a base of 3? And there is. We're going to write it as, so we're going to keep the 3 to the x, and we're going to write 9 as 3 squared. Okay? So we wrote 9 equivalently as 3 to the second power. Now, because 3 to the x equals 3 to the second, they have the same basis, then we're able to say x equals 2. So our solution set is simply 2. You won't write x equals 2 because notice how they want you to express the answer. They give you set builder, which means they just want the answer here. If they wanted the equation, it would say express the answer as an equation. You would actually then write x equals 2. But here they just want the solution set, the value that x is equal to. Okay? Look at number 17. Solve again, same direction, solve using the power of the same base. So we've got 9 raised to the 3x minus 7 on the left side, and we've got equal to 81 on the right side. So there's nothing we can do here. That base of 9, we may have to just hang on to it. Sometimes we have to simplify both sides, but I don't think in this case we're going to have to. So if we can first try to keep the 9 and see if we can express 81 with the base of 9, that's what we'll do. Sometimes, though, you may have to express both of them with a different base altogether. But in this case, 81 can be written equivalently with the base of 9. So we're going to express this. We're going to keep the 9 raised to the 3x minus 7. But we're going to write 81 as 9 to the second power. Okay? So if 9 raised to the 3x minus 7 equals 9 squared, then we can write the exponents 3x minus 7 equal to 2. Now we have a linear equation that we can solve for x. Up here, it was just simply x equals 2. X was already isolated by itself. Here, we got to do a little bit more work to isolate the x to get the answer. So we're just going to use basically our equation techniques that we know to use to solve linear equations. So we'll get rid of the minus 7 by saying plus 7. That gives us 3x equals 9. And then we'll divide by 3 on both sides. And 9 divided by 3 gives us 3. So x equals 3. So our solution set is 3. Okay? All right. That brings us to some now expressions or new equations where we're unable to apply this property. All right, take a look. This equation here is 10x equals 3.52. Okay. There is, unfortunately, no way that we can express the 3.52 with the base of 10. So what we're going to do here instead is apply a principle where we are either applying common logs or natural logs to both sides. Okay? So 10 to the x equals 3.52. What we're going to look at is a new property here where it says, using logarithms to solve exponential equations. Using logarithms to solve exponential equations. Am I still recording? Make sure. Okay, I think I am still recording. I just wanted to make sure. Okay, so using logarithms to solve exponential equations. So here, we would first isolate the exponential expression. Okay. Then, so in other words, we'll get the exponential part by itself. We'll make sure that the exponential part is on one side by itself. Then we'll apply or take the common log or the natural log to both sides. I typically just apply ln, the natural log, to both sides because it feels a little quicker to write for me. Just apply ln to both sides. And then we solve for the variable. We may have to apply a property to where we pull the exponent out, because remember now we're creating a log. So we may have to apply a log property that allows us to pull down the exponent. Take a look at this example here. So we've got 5 to the x power equals 134, okay? Now, there is no way that we can write 134 with the base of 5. If there was in a perfect world, we would. Maybe if this was 125, we would. But unfortunately, 134, we can't express that with the base of 5. So what we do, we take note that the exponential part is isolated by itself. So we then apply either the natural log, which is what I did here, ln, or a common log, log, to both sides. So when we apply the ln to both sides, we've got ln of 5 to the x equals ln of 134. Now, because it's a natural log, we're able to bring down that exponent, which is the x variable. And now we have x times ln of 5 equals ln of 134. And then our last step then is to get the x by itself. So we will divide out by the ln of 5. Because keep in mind, ln of 5 and ln of 134, they're just numbers. They're just decimals, but they're essentially just numbers, just values. So x would equal ln of 134 divided by ln of 5. If they want the exact answer, then you would leave it like this. If they want you to round it to an approximate answer, then you would round it accordingly to how many decimal places they tell you. If you're asked to write it as a solution set, you will leave it in the exact value. So this is the exact answer. This is the approximate answer. Keep that in mind, okay? So let's look at a few problems here, and I think we'll be done. Look at number 18. So we've got 10 to the x equals 3.52. Again, this side, 10 to the x, there's nothing we can do here. It's just a base 10 to the x. In a perfect world, we would write this right-hand side with that same base. But there is not a number that we can express 3.52 with the base of 10. So what we do is we apply the natural log or common log, whichever one you want to do, to both sides. Now, in this case, it would have been easier to apply the common log. So this is applying natural log. Okay. Here I could also apply common log, log. Either one works. And I say I should apply the common log here because if you look, log of 10 to the x power, when there's no index, remember it's understood to be a base 10. So log base 10 of 10, they just cancel out. This is basically just log base 10 of 10 to the x. So that just becomes x. And so x equals log of 3.52. That would be your answer. Because the log base 10 and the base 10 in the exponent part cancel out to just give you x. That's using common log. So when it's a common log, it's a base 10 log. Natural log is ln. Let me work that one as well. Let me work both ways. I'm going to slide this over here this way. So in this case, ln of 10 to the x equals ln of 3.52. I want to show you that it might look different, the final answer, but approximation, it will be the same. Okay, and they would take both answers. My hands. So to clear up. Okay, so this is ln of 10 to the x. Well, here, because I did not apply the common log to get rid of the 10, I have to apply the power rule that allows me to bring down the x. Okay. All right, so that's what I have right now. Then, so I brought down the x as a product. Then I'm going to divide out by the ln of 10. So x equals ln of 3.52 divided by ln of 10. Okay, let me show you both of these, that even though they look different, they are essentially the same rounded or approximate answer. Let me show you. So log of 3.52 is approximately 0.54654. And then ln of 3.52 divided by ln of 10, same answer, 0.54654. Okay? So the computer will take either answer. It may even want the decimal approximation anyway. So either method that you use will produce the correct answer for you. And let me see which one it actually wants. So it does say rounded to 2 decimals. So 0.55. So you're giving the approximate answer here. Okay? And that makes sense because you have options on how you solve it. So you can use either method. The decimal approximation would be the same. Okay? One more example here, number 19. 5 to the x equals 79. Again, this exponential part is by itself already. There's nothing you can do to it per se. In a perfect world, if we could, we would express 78 or 79 rather with the base of 5, but there's no way we can do that. So what we have to do is apply either natural logs or common logs to both sides. If this was a 10, I would use common logs, but since it's not a 10, I'm going to use natural logs just because I prefer natural logs unless it's a base 10 exponent. Okay, so when I apply natural log of both sides, that allows me to apply the power rule where I'm able to bring down my exponent. And so that now becomes x times ln of 5 equals ln of 79. And then I'm able to divide out by ln of 5. And so x is approximately ln of 79. Uh-oh. Parentheses, close it up. Divided by ln of 5. Approximately 2.71. If we're rounding that to 2 decimals, 2.71. Okay. That is all I have for this. I want to make sure I go over all questions that you may have. So we'll talk more soon, looking more at exponential and logarithmic functions. Thank you.